Yeah.
So do you want to wait a couple more minutes, or should I just go ahead?
Okay, Professor, because I think the audience is going to gather. So will that be okay to wait for a couple of minutes?
Oh, sure, no problem.
Right,
Yeah.
okay, thank you very much. Thank you.
Should I try this sharing my?
Yes, sure.
Yeah,
Let me just
try this.
whether you will be able to share. Barış
The
hocam,
slide.
yani yetki verebilir miyiz hocaya? Okay, yes, Professor, you can share your screen now.
Yeah, let me try. This.
From the green tab at the bottom. Yes, now we can see your screen. Yes.
Okay. Is it big enough? I mean, the letters on the slides, are they readable?
It looks good at the moment, actually.
Okay. Yeah.
It looks fine, I think.
Full screen
I can make it a bit larger if you want.
Can you make it full screen, Professor? Would that be okay? Make it full screen?
Yeah. Let me try this. Oh, just a second.
F5?
View'dan.
Full.
Yes, please.
All
Thank
right.
you. Yeah, it's much better.
Okay.
So
just
this is
let
like
me know.
All right.
Just let me know when to start. Okay.
Right, I will. So this is like the first session of the second day of the symposium. So I just wanted to wait maybe for a couple of minutes, then we can get started. I will let you know, Professor, if this is okay.
All right. Okay.
Merve Hocam, herhangi bir sorun var mı?
Hocam şu an bir sorun yok. Şu an sorun yok hocam.
Tamam, sağ ol.
Teşekkürler. Shall we wait for one more minute and then maybe we can get started after 1 minute?
Yeah, sure.
Herkese günaydınlar.
Günaydın hocam. Good morning.
Good morning, everybody.
Good morning. Thank you. So welcome to the second day of the symposium.
Yes. Hocam başlayalım isterseniz. Zaten katılımcı sayımız artıyor.
Okay. So, Professor, if this is okay, I would like to make a very, brief introduction about you, if this is okay with you.
Go ahead. Yeah.
All right, so welcome back to the second day of the Econometrics Symposium. Our first day went quite well, so we hope that the second day is going to be the same. So the day of the symposium, the second day of the symposium is starting with a keynote seminar by Professor Dr. Myung-Jae Lee. He's a professor at the Department of Economics from Korea University, which is based in South Korea. So his primary interests are econometrics and statistics. His specific interests, I would say, please, correct me, Professor, if I'm wrong, but his specific interests include semi-parametrics, non-parametrics, panel data, limited dependent variable, including discrete response, multinomial choice, sample selection, treatment effects, and duration analysis. He was also awarded as the most productive economist in Korea in 2008, and he has many distinct publications, including articles, books in the areas of microeconometrics and econometrics of panel data. So it's such a great honor for me to introduce him. So, ladies and gentlemen, please join me in welcoming Professor Myung-Jae Lee. He's going to talk about OLS and IVE for binary treatment with propensity or instrument score residual. The floor is yours, Professor.
Thank you for the introduction.
My pleasure.
Today, my plan is presenting one of my papers that has been published just a couple of months ago in a stat journal, JRSSB. And if time permits, I'll present another paper that's still at working stage. Usually people do not like presentations on already published materials. But from my viewpoint, I would like the main results in that published paper to be spread among practitioners. So I decided to present the paper. In econometrics, there is a long-standing problem in how to estimate treatment effect if the treatment is binary or more generally non-continuous. And the dependent variable is also not non-continuous, maybe say binary or ordinal, whatever. And today's presentation is how to estimate treatment effect in that kind of cases using simple IVE. So hopefully you can see how treatment effect can be estimated without much problem when you face the situation I just described, namely non-continuous treatment and non-continuous outcome variable. So as I just mentioned, you have a binary treatment that is endogenous, or statisticians would call that confounded. And you have a response variable, outcome variable, or dependent variable that is LDV, that is non-continuous. Let me mention the problems that people face. First of all, I'll use X to just denote covariates, namely the regressors other than the treatment of interest. And let's suppose there is an instrument Z, which is binary for this endogenous treatment. If you have a linear model like this with continuous Y and continuous treatment, then you can estimate this treatment effect in a number of ways. The one is you just do IV, instrumental variable estimation of Y on dx using Z and X as instruments. Okay, that's just basic approach, like econometrics 101 at graduate level. Instead of this, in fact, equivalently, you can try control function approach, CF, which is just OLS of Y on these regressors using this residual as an extra artificial regressor. Here, the residual is the difference between D and OLS fitted value D hat. So by adding this residual, D becomes exogenous. So then you can use OLS. You can also use what I call substitution approach, or some people may say two-stage OLS analog, which is OLS of Y on D hat and X, because D hat is the fitted value. It is essentially exogenous. Now, let's see what kind of problems one has to face if Y is binary, like this. So this is typical threshold crossing binary response model. And D is also binary like this. As you can see, the parameters for Y, they are denoted with betas, and the parameters for treatment, they are denoted with alphas. Okay. And U is the Y equation error term, whereas epsilon is the equation error term. So both are binary, and if you try to do the same as done in for continuous case, then you will run into problems. First of all, this IV is not applicable because you have a nonlinear model. And secondly, if you try to apply control function approach, you may try to do a probable logic for Y using these things ZX and epsilon hat as regressors. However, since epsilon is this error term in this binary response model, you cannot actually find epsilon hat. So despite that, some applied people actually proceed this way. This is not valid because epsilon hat is not identified. And thirdly, if you try to apply a substitution approach, then you would try to do probable logic of Y on T hat and X. But if you try this, I mean, you are replacing the endogenous regressor treatment with its fitted value. But this operation actually adds this difference to the model error term. But as you can see, even if U is normal or logistic, this error term is not continuously distributed. So this sum, it cannot be normal nor logistic. So these show how this conventional approaches for continuous case actually fails when you have binary treatment and binary outcome. Oh, by the way, if you have any questions, just ask me at any time. We have just too much time.
Thank you, Professor.
Yeah. Okay. Following this kind of the usual approach in treatment effect analysis, let me define potential treatments as D0, D1. So you can think of this as say randomized encouragement to take the treatment, and this will be the treatment choice without the randomized encouragement, and this will be the treatment choice with the randomized encouragement. And I can also define potential responses Y0, Y1 corresponding to the treatment. And let me introduce well-known terminology that is a complier. Compliers are those who take the treatment only when Z is equal to 1, only when encouraged. And otherwise, if not encouraged, the person, the complier, would not take the treatment. And this definition appears in this paper. And a condition that's usually imposed is this monotonicity condition. Namely, you are more likely to take the treatment if encouraged than otherwise. In the paper that I published in July this year, I show a linear representation for, surprisingly, any outcome variable. I mean, this can be binary or whatever, ordinal or censored. Regardless of the form of y, you can always have this equation where mu0x is, you can think of this as an intercept, and mu1x is the slope of d, that is the treatment effect. In fact, the paper shows mu1x takes this particular form. If you look at this definition, that is the treatment effect given x, some individual trace, and given that the person is a complier. So this is the treatment effect on complier. And usually this is a nonlinear function of x, so you'll have a heterogeneous treatment effect right here. And u takes, this is an error term, takes some particular form. However, u satisfies this conditional moment condition that u given instrument and covariate, the expected value is 0. By the way, this is not a structural form, namely data generating process. But this is not a typical reduced form either, because it contains structural form parameter of interest, which is mu1x. So maybe it's better to call this equation reduced structural form. And if you apply some polynomial approximation for these functions here, then you would end up with a linear model for Y, and then you can apply IV. So since that's a fairly straightforward approach, let me explain what is new in this paper using this linear representation. So what the paper suggests is an instrumental residual estimator. So let me introduce instrument score, that is the conditional mean of instrument given X. This is very much like a propensity score. Propensity score is a conditional mean of treatment given X. And this, I call this instrument score, but there are some papers already in the literature using this name. So if you look at this formula here, so this estimator is a sample version of this ratio. And if you look at this ratio, you can actually see Z minus this instrument score is used as an instrument. So that's the treatment, that's outcome. You can ignore E of Y. I mean, if necessary, I can just set this to 0. So then the whole thing becomes the simple IV formula. And only difference is that instead of using Z per se, I'm using Z minus instrument score. Why am I using this zeta X? The reason is that by subtracting this, I can actually get rid of this unknown function of X in this linear representation. So zeta X, the role of zeta X is removing that unknown intercept. So you can easily imagine a sample version of this replacing instrument score with, say, logit or probit. So you just apply logit or probit to Z on X, and you get a fitted value, namely the predicted probability. And then you subtract that from instrument, and you do this IV. Okay. Now the question is, when the effect is heterogeneous like here, what do we estimate by using this simple estimator I call IRE? As it turns out, IRE estimates a particular weighted average of this unknown heterogeneous effect. And the weight actually looks like this. So weight is proportional to the covariance between treatment and your instrument. So in a way, you can say that the weight takes care of a weak instrument problem, because if the instrument is weak for some people in this sense, then the person receives a low weight, almost 0 weight. Okay. But actually, if you go deeper, this covariance between instrument and treatment can be written like this. If you look at this, it consists of 2 terms. The first one is the complier probability. The second is the instrument score times 1 minus instrument score. And if you think of this function, if you look at this function, this is quadratic in instrument score. And if I draw a figure, it actually goes up and down like this. And this function reaches its maximum when instrument is 0.5. So so the maximum weight goes to individuals with this being around 0.5. I'll talk about this function more in detail and shortly in the next slide. But anyway, let me just reiterate the simplicity of this estimator. You obtain this from longitudinal probit, and you do IRE with y minus y bar. You can even drop this y bar on DN this instrument. Asymptotic distribution is in the paper, and it's easy to get, but you can also use Bootstrap if you want. Now let me turn to this particular weight. It is called overlap weight. The name appears in this paper, but this has been used in the literature. Although this, I mean, if this name was not that explicit. To appreciate overlap weight, or W, let's consider exogenous treatment for a while. When the treatment is exogenous, treatment becomes its own instrument. Then everybody is a complier. So the probability of complier is equal to 1. Since the probability of complier equal to 1, so in this expression, this is equal to 1, and only this remains. Covariance between instrument and treatment becomes variance of D given X because of this. And denoting the propensity score as pi sub X, since D is binary, this variance is this PS times 1 minus PS. And overlap weight takes this form. And as I mentioned, this function, this quadratic function as a function of PS, if you plot it, the function goes up and down over pi x ranging 0 to 1, and it reaches its maximum when pi of sub x is 0.5. So what it means that when you do, say, matching or some other form of estimation, individuals with PS near 0.5, they receive the maximum weight. That is good because those people with PS around 0.5, they are kind of indifferent between taking or not taking the treatment. So in some sense, overlap weight gives this randomization flavor, even if you have an observation, data set. By the way, I introduced the linear in D representation when D is endogenous, but if D becomes exogenous, I have this representation, which is a special case of the earlier representation in 2018 paper. And in this case, it's straightforward to show the intercept. The unknown function is conditional mean of y0 given x. And slope of D is this conditional effect. And error term has conditional mean 0 when conditioned on this D and X. And for this exogenous D case, this instrument residual estimator becomes OLS with propensity score. And if you look at this formula, this is just OLS with D minus propensity score as the regressor. And again, you can drop this expected value of Y without changing much. And this paper shows this simple OLS actually estimate this weighted average of this heterogeneous effect, where weight takes this overlap weight. So here I list some advantages of overlap weight. First, as I mentioned, this function attains a maximum at this value. So if you consider, say, propensity score matching, individuals who best overlap with the opposite group, they receive the highest weight. Individuals with propensity score near 0 or 1, they have the worst overlapping with the opposite group, and these people, they will get almost 0 weight. And the second advantage is that I guess I also mentioned this point, that if you are near 0.5, then you could have gone either direction of taking or not taking the treatment. So then it is sensible to think of randomizing the treatment. And the opposite is true for those with PS 0 or 1. You may like this effect on population, so-called, which is just average of this conditional effect. But in fact, the so-called effect on population, it makes a poor marginal effect, because some subpopulations are unlikely to change their treatment status no matter what. Namely, people with these, they are unlikely to change their treatment status. And it's better not to count them in when you weight average this heterogeneous effect. And overlap weight, it overcomes this problem. And also, as shown in this JSR paper, overlap weight can make resulting estimator efficient in some sense, and balance X better. And also, if you apply other than matching, such as what is called regression adjustment or regression imputation, then well, when you use this approach, you specify this model for Y. But if you attach overlap weight, this estimation becomes robust to misspecifications in this outcome model. This is what's known in statistics literature, like this paper in Statistics in Medicine. So let me turn back to the endogenous case and the IRE, the parameter that IRE estimates. It is weighted average of unknown heterogeneous effect, where weight takes this form. I already explained this is overlap weight and why it can be beneficial to use overlap weight. So if you take instrument as the deep treatment, then its overlap weight in terms of this deep treatment appears right here. And if you do not like this weighting function, you can actually do weighted OLS, weighted IVE. That looks like this. If you look at this, the IRE estimator is modified by dividing the denominator and numerator with this estimate for overlap weight. If you apply this weighted IRE, then you will be estimating the simple average without this particular weighting function. But however, if you actually apply this, this does not always work well, because this estimator, I call it WIR, is on IPW, inverse probability weighting estimator, which has the well-known problem that if the denominator, if the weighting function is close to 0, the whole thing just can blow off. Okay, so then you may get strange numbers, and then you have to introduce trimming to remove weighting functions close to 0, and that introduces some arbitrariness. So my preference is just using this instead of this weighted version. I don't know why I have this red line on my screen, but I don't know how to get rid of this red line. I'll just go along with this. Let me introduce one estimator in the literature. There was, I guess due to the time concern, I'll skip this estimator. It is closely related to IRE, but it estimates this complier effect. It was proposed by Tan in JESHA 2006, and also proposed much later by these people because they were not aware of that the same estimate was proposed a long time ago. But I'll skip this slide due to the time concern. I'll also skip other approaches. Okay, how do we actually implement IRE? Let me introduce one modification. I mentioned that I use this as an IB, where this is the instrument score. So probit of Z on X. Oh, there is this probit of this instrument score. So that's my IV, my treatment. The modification I'm introducing is, instead of using Y or Y minus Y bar, I'm using something more complicated. What is this? Here is the explanation. After I obtain this probit estimator of Z on X, I form polynomial functions of this probit regressor. Okay, that this is the same probit regression function of here, and I use the scaled version and so on, all the way up to arbitrary Q. So then I do OLS of Y on this to get these OLS estimates. So what appears here is the OLS fitted value, say y hat. Okay. This is actually not essential, but if you do this, small sample performance will improve. And also, if you use this, yeah, there are explanations. If you set Q equals 0, then you are using Y bar right here. But non-zero Q gives better performance when this instrument score is misspecified. I mean, if you apply probit or logit, you can misspecify the function. So if that happens, that can bias your estimates. And by using this, the bias becomes much smaller. In fact, in the literature, this kind of procedure subtracting conditional mean from y variable, and then your instrument or regressor is called double. They are called double orthogonalized variables, and this double orthogonalization it gives some advantages, some improvement on your estimation procedure. Yeah, so if you want to implement this estimator, you do say probit or logit of Z on X to get this. And then you form this polynomial functions of this regression function, say order 2, order 3. You do OLS of Y on this to get OLS estimators, and subtract the OLS fitted value from Y. And finally, IV of this on D with this as an instrument. So not much difficult here, right? All you have to do is just probit and probit, OLS, and then IV. So it's fairly easy. Oh, here is the empirical example in the paper. In this example, D is the flu vaccine, and Y is whether the person is hospitalized or not because of the flu. I mean, given the recent COVID pandemic, this example looks quite appropriate, right? And Z is randomized encouragement to take the vaccine, right? And the same data have been used by these people. And here are some descriptive statistics like mean Z, D, Y, and average age 65, 67% women. Here is race, white people. This is COPD, chronic, some disease, lung disease, some heart disease, renal disease. And so I do probit of D on X. This is for propensity score, where X consists of these variables. Here is the probit of Z on X. That's to construct instrument score. I don't know why, but although Z is supposed to be randomized, I see some fairly large T value for this female, although pseudo R-square is fairly low. And if I do probit of D on instrument X, instrument is highly significant. It's justifying the usual inclusion restriction for instrument. So anyway, I applied the estimators to this data. And this IV0 is just simple IV, ignoring covariates. That is fine because we have a randomized data. You can just do simple IV with this as a regressor and this as an instrument. So that's simple IV. IV. This is IV controlling covariates. Okay. But this is randomized study. Controlling covariates hardly makes any difference. They are almost same. This is IRE with Y minus Y bar as the outcome variable. And you get almost same result. And IRE with Q being 2. So going back here, I have this OLS fitted value using second order polynomial here. But this IR, the second order is again almost same. This is the weighted version to remove the overlap weight. But as I mentioned, because of the the problem of denominator being close to 0, this is somewhat erratic. The 10th estimator that I skipped is again very similar to this. 10th estimator this is also IPW, so it has trimming constant tau. Namely, you throw away observations with the denominator, the weighting function smaller than these numbers. The paper has another empirical example where instrument is not randomized but observational, and in that example, the estimators they are much different from one another. Yeah, I'll skip this part. Yeah, let me summarize the paper I presented and the estimator. This works for any outcome variable, almost any. I mean, because the heterogeneous effect was defined as y1 minus y0. And for that to make sense, some restrictions are needed, but virtually almost all outcome variables are allowed. And treatment is binary and endogenous, covariance X, and instrument Z is binary. And this situation posed a long-standing problem in econometrics. I mean, how to find treatment effect in this case. And here is the summary of IRE. You do probit of instrument X to get probit predicted probability. And you form this function with second or third order. And then do OLS of Y on this to get gamma OLS estimates. And you construct this modified outcome variable and do IV of this on D using this as an instrument. And this estimator is consistent for overlap weighted heterogeneous effect. And the weighting factor, in simple term, it is proportional to the covariance between instrument and treatment. But if you look deeper, that covariance can be written in this way.
Professor, would it be okay to raise a question?
Yeah, sure, go ahead.
Yeah, I mean, when we go back to the previous table, you have recently showed us where the treatment effects were quite similar.
Yeah.
Right,
Yeah.
this one. I think that was the sample size was roughly about 2,800, I guess. So I just wonder whether, so I just wonder whether the whole results are sensitive to the sample sizes. Like, I just wonder sample size sensitivity could be a concern, or that's kind of the question I come up with. Because
I
the treatment
forgot-
effects are quite. Uh-huh.
Yeah, I forgot the sample size. But
I think it was
probably,
roughly
a couple of
2,800.
thousand. And the reason you get so similar estimates is that it
Mhm.
basically you have a randomized instrument. That's why.
Right. I see. So I was kind of
Yeah.
thinking whether it could be something to do with the sample sizes, but as you said, yes. they-
No. It
That's-
actually has to do with
Yeah.
the randomness of this
Right.
instrument.
Yeah, sure. Thank you. Thanks. Thank you.
Yeah. Let me then move on to my second paper. I have only 5 or 6 slides for this, so I can finish it in time.
We still have time. Yeah.
Well, myself, I hate long seminars, so I try to, finish in time.
All right.
Okay, here, this is a different problem. Here, the problem is that there is no instrument. You are worried about endogeneity of your treatment. So then usual approach in econometrics, you use panel data and you allow fixed effect. You take the difference of your linear model and you get rid of fixed effect, and endogenous problem is solved. And that's the scenario that many applied researchers follow. So let me look at that issue. I have, there is no instrument, but now I need a continuous Y. And here is my model. And if you look at here, now the Z is not an instrument. This is just a covariance. My treatment, fixed effect, this usual error term. The error term conditional mean given treatments and the covariance are 0. So delta is the source of treatment endogeneity. And this functional form is unknown. However, now I can, this nonlinear function can return in this way without losing any generality, because I can rewrite this function like this. I mean, if you compare right and left, right hand side and left hand side, when t is equal to 0, you only have this left, which is equal to this. And when t is equal to 1, you have this canceled by this, and only this remains. So this shows this nonlinear function can be written in this way without losing generality. So I redefine this as mu and this as mu d. So now I replace this function with this, and that gives me this equivalent model. Well, this is a fairly well-known kind of standard trick going from here to here. Now I take difference on this equation, and that will remove this, right? So I have then delta y and also delta u defined like this. The problem is this part. If I take the difference, then this becomes this. Let me define zi as collection of all time constant and time varying regressors. So this is a notational matter, and this becomes this. And here is the headache. I mean, if you take the difference, the second period term expression appears here. And this is the first period expression. So essentially, you end up with something like this, difference of the treatment effect part. But this is not what you want, because what you want is something like this, because effect is treatment effect is time varying. And if you want some representative effect, you would want to have a time averaged effect, not time difference effect. So the main issue in this approach is how to turn this kind of difference into something like this, so that I can say, this is what I want. Okay. And in the literature, there are many complicated non-parametric estimators that are hardly ever used. But what I propose in this paper, which is still a working paper, is just following OLS. The OLS goes like this. You obtain this period T propensity score. Okay, this is propensity score at period T. And you take the difference of the propensity score. Okay, this is propensity score difference. And you construct this regressor, which is del treatment change minus this propensity score change. Then you do OLS of delta Y on this. This is simple OS. There is only one regressor here. The reason for this appearance is, again, is to get rid of this. This unknown function is here, and to take care of, or to remove this function, I'm using this propensity score residual difference. This is main idea, but again, a modified version with this as the dependent variable works better. For the same reason, I used modified instrument residual estimator. And here, pi sub z is two-dimensional. It's a collection of both periods propensity scores. So if you look at this OLS, this is the regressor part, and here, and this is the dependent variable part. And this panel data OLS, I mean, once you take the difference, this just becomes cross-section single equation. Surprisingly, this is consistent to a weighted average of first period effect and second period effect. The weight is proportional to variance. Okay, if you look at this weighting function, it is actually a variance of this treatment given Z minus covariance of two periods treatment. So surprisingly, that the difference equation gives something like this. I ended up finding an expression similar to this. This is a simple average of two periods treatment effects, right? And this is a weighted average of the two periods treatment effects. So the reason I put forth this result is that, I mean, you do a fixed effect estimation, right? When you do fixed effect estimation, you do OLS of delta Y, delta D on, say, delta regressors. But you do this under the assumption that treatment effect is a constant, right? But in reality, treatment effect will never be a constant, right? If you take a medicine, effect varies across individuals. So the reality is that almost always treatment effect is heterogeneous and unknown. So despite that, you apply this fixed effect estimator. There is OLS of delta Y on delta D and delta X. Then what do you estimate? The answer is actually, what you estimate is very close to this. As long as this propensity score difference is similar to a linear projection of delta D on delta Z. So this condition is often holds. So under this, then the usual fixed effect estimator, it gives you actually this. That's the one answer. And another OLS proposed in the paper is the same OLS, but now we use only observations with this, observations with their treatment changing. If you do that, you get to estimate something a little different. Then you get to estimate something like this. This is the time averaged effect that is weighted by PZ. PG is defined right here. Okay. For individuals whose treatment status changing, this is the probability that the person takes a treatment in the second period, but not in the first period. I mean, maybe this expression will help you better. So the PG can be written like this. The probability of no treatment in the first period and treatment second period divided by 0, 1, and 1, 0 probability. And that is piece of Z. And so that OLS is consistent for this overlap weighted average of 2 periods. And if you want to remove this weighting function, you can again do weighted OLS to your panel, this panel OLS, I mean this approach. But then weighting also then brings up this well-known, too small denominator problem. So this unpublished paper introduces 3 estimators. One is that this OLS. Second is same OLS but dropping samples without treatment variation. And third is weighted version of this to get rid of this overlap weight. So let me just show some empirical example here. We got some data, 2 waves from South Korean youth panel, and first wave is 2016, second for 2019. D is the labor union membership. So, and Y is log wage. So you are looking at so-called labor union wage premium. How much more wage do you get by joining a labor union? There are about 3,600 individuals in this panel data, but only 9% has their treatment changed across 2 waves. So when I look at this small sample, I have only much smaller sample size. But anyway, here are the estimation results with Y being log wage, and here is the estimate 1, 2, 3. Q is the same, this polynomial order. And bottom here, there is this usual fixed effect estimate. And if you look at this, not much difference. The usual fixed effect estimator is 0.4% effect. The variance weighted effect is around 4 to 5%, and the other estimators are also they give similar numbers. I guess that's all. I mean, yeah, that's the end of my slides. Do you have any questions?
All right. Thank you very much, Professor. So we still have time. I wonder whether there are any questions from the floor. Are there any questions or any comments from the floor? All right. So, Professor, thank you so much. Please accept our sincere appreciation for this outstanding and enlightening talk. As you have mentioned in your talk, it's really challenging, especially for econometricians, to find the effect of an endogenous binary treatment on a limited dependent variable. So today's talk, the slides you showed gave us a very close look at how to use OLS and the IV in this context for both cross-sectional and panel data in the second part of your talk. So thank you so much for sharing your time and your research. It's such a great honor and a great pleasure for us to welcome you today. Thank you so much. Thank you very much, Professor. Thank you. Thank you. We hope to see you, maybe meet you in person, maybe in the future when there is no, COVID.
Right.
We'd like to welcome you in person.
Thank you.
Thank you.
Very much.
You have a lovely day. Thank you very much. Bye. Thank you. The floor is yours, Deniz.
Hocam keynote speakerlarımızın olduğu zamanlarda zaten oturum koymamıştık. Şu an 11.30'da Seher Hoca'nın oturumu var. Ana salonda ve genç oturumlarda da var. Sadece 2 oturum var bir sonraki 11.30 oturumumuzda. Bu kadar hocam. 11.30'da görüşmek üzere.
11.30'da görüşmek üzere. Hoşça kalın.
Teşekkür ederiz. Hoşça kalın.